This is the great sentient wake of Sir Isaac Newton, the inventor of the Fig Newton. No, not really, but still, he's important. Not because he may or may not have invented a semi-popular snack brand, but because of his many contributions to modern physics, including his theory of gravity. Sir Isaac Newton once wrote a book called Mathematical Principles of Natural Philosophy. In it, Newton uses his theory of gravity to explain why large objects stay in circular orbit, such as the moon going around the Earth or the Earth going around the sun. His theory states that all particles will attract each other to a degree that is proportionate to their masses and inversely proportional to how far apart they are squared, meaning that the larger the two masses are, the stronger the gravitational force will be between them, and the farther away the two masses are, the weaker the gravitational forces will be between them, and vice versa. While Isaac Newton had his theory of gravity, there was a German scientist who had a different theory, the theory of relativity, and his name was Albert Einstein. Einstein was a German physicist who came up with the theory of relativity and also discovered the equation for it, of E equals mc squared, where m, which represents the amount of mass, is multiplied by c squared, which is the speed of light, squared, to equal E, which is the total amount of kinetic energy. When you convert a part of matter to pure energy, the resulting energy is moving at the speed of light, which means that energy and mass are interchangeable. They are different forms of the same thing, and during certain circumstances, energy can be mass and mass can be energy. This led to the theory in which gravity can be thought of as movements of particles through a curved space-time. Space-time consists of 4 different dimensions, 3 wares such as an x, y, and z which represent location, and a when, which represents the time in which things happen. Flat space-time is an idealistic space-time, a space-time that exists without the presence of mass to distort it. Curved space-time, however, is what happens when you apply mass to a flat space-time, which is the state of our current reality, which you can see represented in the 2 pictures here. In the picture to the left, you see a demo for the curvature of space-time in which they use a heavy ball to create an indent in the fabric, where the fabric represents space-time and the heavy ball obviously represents mass. While the picture on the right is a representation of Earth in curved space-time. This shows how the mass of the Earth causes the particles to change or curve their movements due to the presence of Earth's mass. When an object orbits another object in space-time, it is not gravity that is keeping that object in orbit, but instead the movement of particles in space-time causing the object to orbit the other one. The circular form of this orbit is caused by the curvature of space-time around the 2 objects due to their 2 masses. Matter causes space to curve. It is assumed that gravitation is not a force, as understood by Newtonian physics, but a curved field, an area of space under the influence of a force in the space-time continuum that is actually created by the presence of mass, meaning that gravity is non-existent. Objects move straight in a space-time until they come along a mass large enough to curve space-time and change the direction or movement of the object. Gravity does not exist in general relativity. Instead, the Earth is exerting a constant force outward and not inward. The more mass an object has, the greater it is that the curvature of space-time around that object will be. As you can see here, the Sun, which has a mass of 1.989 times 10 to the 30th kilograms, only causes a slight curvature in the space-time when compared to a white dwarf. A white dwarf causes only half the amount of curvature as a neutron star, while a black hole causes more than twice the curvature of a neutron star. In general relativity, space contracts near mass and dilates away from it, meaning the closer you get towards mass, the more condensed the flow of particles moving around it will be, creating a stronger downward force, creating what would be called, in Newtonian physics, gravity. On the other hand, you have time, which dilates near mass and contracts away from it, meaning the closer you get towards a larger mass, the slower time will move, while the farther away you get, the faster time will move.